Last talk of this session, I'm Shansu Park from KAIST, together with a lot of people. Please.
Thank you for your info. So, as I informed, my name is Chansu Park, a freshman of Graduate School of Computing at KAIST in Korea. So, I will introduce our present work named as Computable Operations on Complex Subsets on Metric Spaces with applications to fractal distance and shape optimization. So, here is our outline. So we first recap the basic definitions and some properties of previous works, and then we extend and newly define some new concepts for our research on the complex metric space. And then we will prove some operations are computable on that complex metric space, and then extend to the higher type computations. As a term of application, I will only introduce about shape optimization. So we aim to extend theory of computation on real numbers or bounded closed Euclidean subsets or continuous real functions to such a complex metric spaces. Actually, the theory of the computability and complexity theory on such a general complex metric space were not concrete because previous works doesn't define efficiently. So we extended many definitions reasonably. So in this talk, I will introduce lots of definitions and theorems. So almost all of us know what is the name of the real number. You can see the interval strictly converges to the point x with the error bound by half when we increase the step further. Also, the similar idea can be applied to the open set subset of the Euclidean space. Using this definition of name, we can also define what is computable. So the point is computable if and only if it admits a computable name. And the partial function is computable if some machine maps the name of the domain to the name of the function value. But just saying it is computable is insufficient. We also have to know how to compute. So here's the computing. Computing a real number is to give such a name, and we have to admit that it converges to the original real number with error bound half by step, and also that idea is also can be applied on there. So here is an example as an addition. Here we introduce a weird rounding function, but it is reasonable after we calculate the errors of each step like this. There's also an important concept, modulus of continuity and binary modulus of continuity. So the modulus of continuity function is such that it converges to 0 when the parameter is 0, and the distance between two function value is bounded by that modulus of continuity. It is also easily converted to the binary modulus of continuity. So there are trivial example which is Lipschitz continuous. So for that constant, the mapping x to 2kx is a modulus of continuity of f, and also a mapping n to n plus k is a binary modulus of continuity. There are also two definitions like Bayer space and suprema metric. Actually, previous works also worked on such an Hausdorff hyperspace, so we already know what is the Hausdorff distance. From the one point, we can reach such a set by taking its infimum, and then we take the supremum for entire set, and then to make it is symmetric, we take the maximum. So by equipping Hausdorff distance on the set of non-empty closed subsets of X, we can define it is a Hausdorff hyperspace over X. There are many such lemmas related to the Hausdorff hyperspace. So common works extended like from d-dimensional unicube to arbitrary compact metric spaces, and extended dialectic rationals to the canonical countable dense subset. But furthermore, we proposed conditions that formalize and generalize numerical grids to more general compact metric spaces and higher type spaces. We mainly considered a relaxation of hierarchical space partitioning whose subsets are closed both, and they can overlap with each other as long as their centers are sufficiently close. So for the entire talk, we will fix a compact metric space which diameter is less than or equal to 1. So here are the new definitions, M covering and eta separated. We defined an M covering of X as a subset of Xm that the union of all possible balls includes X as a subset. Also, for that Xm, we define eta separated if the two distinct points have its distance at least 2 to the minus eta. In this diagram, I pointed such points and draw the open balls. Then you can easily know that it is such an M covering and eta separated. And now we equipped a partial dense enumeration on that compact metric space and also equipped a strictly increasing function. And then we change it eta from natural number to the natural function. Then that given 4-tuple is called a presented metric space if for every m, the image of the enumeration constitutes an M covering of X. And furthermore, if we assume that is injected, that it is eta separated, if for every m, that image also constitutes an eta m separated M covering of X. So we successfully equipped the partial dense enumeration and such a strictly increasing function on the compact metric space. Then how can we roll about the computability on there? So here is our new definition, computably compact. It is called computably compact if both a domain of enumeration and the given strictly increasing function are recursive, and the given set which takes such a 5-tuple is semi-decidable. So for example, we already know what is the set of dialectic rationals, and then we can divide into such sets Dm whose denominator is 2 to the Dm, and then we define a strictly increasing function as m plus 1, and then inductively define the enumeration as like this. Then we can easily know that it is M-separated computably compact space. Note that if we change A by 1, then it differs by 2 to the minus m, which makes it is M-separated. So we can successfully define what is the computably compact, and then we define a name for that spaces. So the point of X has a name as like a sequence, which is an element of the intersection of the domain of enumeration and the set of natural numbers bounded by 2 to the dm. And also, its enumerated value and the original value has distance and most 2 to the d minus m. So you can easily know that following these nearer points makes a name of the point of x. Also, we defined a name for partial mapping, but we have to recall such a weird variables. So we defined xcdm as a set of integers which is bounded by this set and also satisfies the distance is bounded by 2 to the minus n. And then we we composed them by increasing order of m to get xcd, and then we also take a union of full set w to get wcd. And also we know the set of finite initial segments is defined as this. And